How do you think? I mean, really, how? It's such a basic question we hardly ever stop to ask. Every day, you're making thousands upon thousands of decisions, and most of them you don't even notice. But underneath that simple, effortless surface, well, that's where one of the most complex systems we know of is hard at work. Today, we're going to peel back the layers on the hidden mechanics behind every single choice you make.
Just think about it for a second. Coffee or tea? Right now. Chances are an answer popped into your head almost instantly, right? It feels completely automatic, like it takes no effort at all. You subconsciously weigh your preferences, maybe think about what you had yesterday, the time of day, and poof, a decision just appears. But that feeling of simplicity, that's actually a beautiful illusion. Because that simple choice is actually the result of this massive coordinated symphony happening inside your skull. I mean, how does a network of 86 billion individual neurons, each one talking to thousands of its neighbors, somehow come to a single unified conclusion? That is the incredible mystery we're diving into today.
Okay, so, Section 1, the adaptive synapse. To understand the big picture, we've got to start small, with the fundamental building blocks of how we learn. The absolute key idea here is something called synaptic plasticity, and it's a really profound concept that's actually pretty simple. The connections in your brain aren't set in stone, not at all. They are constantly changing, constantly adapting. Every single experience you have, every choice you make, it physically rewires your brain, making some connections stronger and letting others fade away. This, right here, is the very essence of learning. Way back in 1949, a neuropsychologist named Donald Hebb came up with this really elegant rule for how this all works. It's a principle so fundamental it's often summed up with the phrase, neurons that fire together wire together. You've probably heard it before. This is heavy in learning, and it's basically the bedrock of modern neuroscience. All it means is that when one neuron helps another one fire, the connection, that little synapse between them, gets a tiny bit stronger. So the next time you think about coffee, those coffee neurons fire up, and the pathways that lead to you saying yes are just a little bit faster, a little bit more efficient than they were before. Your brain is physically changing based on what you do.
All right, Section 2, models of the mind. So we have this biological rule. But how in the world do scientists take that squishy biological concept and turn it into cold, hard math? Well, welcome to the fascinating world of mathematical psychology. This is a field where researchers, pioneers like Tversky, Townsend, and Ratcliffe, aren't just content to observe what we do. No, they are trying to write the actual equations of thought. They want to build formal mathematical models that can actually predict how we see, learn, and decide.
And, one of the ultimate tests for these complex models is to see if they can accurately describe something as basic as our coffee or tea problem. Can you really create a mathematical formula that behaves just like a human brain when it's faced with a simple choice between two options? Well, it turns out you can. And one of the most successful models for this is the diffusion decision model, developed by Roger Ratcliffe. It's brilliant. It basically treats a decision like a race. You start in the middle, totally neutral, then your brain starts gathering evidence, memories, smells, feelings that push you toward one choice or the other. And the moment the accumulated evidence for one option hits a certain threshold, bam, the decision is locked in. What's so cool about this is that it doesn't just predict what you'll choose, it predicts how long it'll take you, giving us this incredible window into the mind in motion. So here's the real takeaway. Mathematical models like this one are a total game changer for psychology. We're moving beyond just describing what people do. We're actually creating a formal process that can make incredibly specific, testable predictions about our choices. It's like we finally get to peek under the hood and see the engine of cognition itself. On to Section 3, bridging brains in AI. Now, what's really fascinating is that these models of our wetware, our biological brains, didn't just stay in psychology labs. They became the actual blueprint for building artificial minds. I mean, look at this. The line from brain theory to AI is a straight one. It all starts with Hebb's biological idea in 1949. Then, in '82, John Hopfield shows that computer networks built on this exact principle can do amazing things. By '86, this whole idea of brain-inspired AI explodes in popularity. And then, by '98, we get reinforcement learning, which is basically a formal way to teach these systems to learn from rewards and punishments. Just like we do.
The parallels are just stunning. It's almost a one-to-one translation. Our biological brain has neurons, and artificial neural network has nodes. We have synapses, they have weighted connections. Our brain's amazing ability for synaptic plasticity, well, that's just their learning algorithms. And that mysterious thing we call cognition, in their world, it's called emergent computation. We are, quite literally, building artificial intelligence in our own biological image.
Okay, so final section, what's next? Because understanding all these mechanics has some really profound implications for the future of the mind, both ours and the ones we build.
So why does any of this really matter? Well, because when you start to understand the rules of thought, you get a step closer to understanding consciousness itself. It means we can build more powerful, more adaptive AI. It means we could potentially diagnose and even treat cognitive disorders by seeing exactly where the computational process goes wrong. We can design better ways to teach that work with our brain's natural rules, not against them. And ultimately, we get to the very heart of what it even means to make a choice.
And in the end, it's just this beautiful synthesis of ideas. Yeah, the brain is a kind of computer, sure, but it's so much more than that. It's this incredibly elegant, self-organizing biological machine, one that uses these simple, adaptive rules to learn, to grow, and to somehow create meaning out of all the chaotic information the world throws at it. And that really leaves us with one final awe-inspiring question. As we get better and better at mapping these processes, at writing the formal rules of thought, what does that empower us to do next? What comes after that? The possibilities? Well, they're about as vast and as complex as the brain itself.